Good morning, and thank you for the opportunity to present this work. Its full title is Information-Energetic Thermodynamics, a public benchmark demonstration of the VIRR framework for physical decision efficiency. On the first slide, I want to place the audience immediately inside the real subject of the work. This is not just another metric for energy efficiency. It is a change in the question. We usually ask, how many operations does the hardware perform per watt? This work asks, how many physically valid decisions are produced per joule? The full title says exactly that. Information-Energetic Thermodynamics means that I treat computation as a physical process, not as abstract symbol motion. Every decision has an energetic cost, a temporal trajectory, a noise background, and a stability condition. Public benchmark demonstration means that one layer of this framework is shown on public benchmark data, specifically ML-Perf Tiny, version 1.3. And physical decision efficiency means that the goal is not to measure raw activity, but the efficiency of a stabilized outcome. The basic problem is simple. Ops per watt, tops per watt, and energy per inference are useful, but they often count arithmetic activity. By themselves, they do not say whether the physical process produced a stabilized, irreversible informational outcome, and precisely in that gap, hallucinating bits appear. States that look like information but are not stable, distinguishable, or retained enough to carry the responsibility of a decision. This is why I introduce VIRR, the valid, irreversible resolution rate. In this talk, I will explain it simply as the number of accepted stable outcomes per joule. More precisely, it is the rate of valid, stabilized, irreversible events divided by the supplied power inside the declared energy boundary. A crucial point is that the work separates three levels. Full VIRR is the physical laboratory ideal. It would require trajectories, retention, distinguishability, and entropy evidence. Task VIRR is the publicly auditable benchmark layer, completed task outcomes satisfying the benchmark rule normalized by energy. Estimated VIRR is a weaker operation-derived calculation from tops per watt and declared operations per output. In the public data part of the work, I use 27 ml/perf tiny power results across 5 workloads. Task-level VIRR spans a wide range, approximately from 2.73 times 10 to the minus 2 up to 3.17 times 10 to the 4th benchmark outcomes per joule. This does not mean that ML-Perf measures microscopic entropy. It means that public data already allow a first honest audit of the outcome per energy layer. The work then shows one more thing. Once we include valid output probability, rejected transitions, retention, conversion, and control overhead, architectural rankings can change. A system that looks excellent under raw energy may not be best under accepted stable outcomes. It may simply be very efficient at producing activity, heat, and hallucinating bits. In the worst case, these are not efficient computers, but expensive heaters with a very sophisticated output format. So my central thesis is this: computation is not activity without a body. Computation is a physical event. It must pay energy, survive noise, persist in time, and pass the conditions of validity. The rest of the slides unpack exactly that sentence. First, the difference between activity and decision. Then the physical validity tests, the energy ledger, the public data, the sensitivity analyses, and finally the validation ladder toward full VIRR. We can now move to the second slide, where the first part of that thesis begins: why counting operations is not yet counting decisions. The second slide places 3 ways of thinking next to each other. Tops per watt asks, how much arithmetic activity do I get per watt? Energy delay product asks, what do energy and time cost together? VIRR asks a different question. How much of that activity became an accepted stable outcome? I do not mean that tops per watt or energy delay product are bad metrics. They are not. They are useful engineering tools, but they do not ask the final question that becomes increasingly important in emerging architectures. Did the physical state actually survive as a decision? In deterministic CMOS, we can often treat validity as practically 1. The outcome is robust, logic levels are clear, and conventional metrics make very good sense. But in analog computing, compute in memory, resistive RAM, neuromorphic systems, and stochastic devices, outcomes are not born in such a clean world. They are born in noise, boundary states, retention windows, and conversion stages. There, a system can emit a state that looks like a bit but is not stable enough to be an outcome. That is a hallucinating bit. It is not a metaphor for a software bug, it is a physical situation. The signal has the shape of information but not its legitimacy. This takes us to the third slide, where I define what a candidate output must satisfy before it can be counted as a decision. The third slide shows the gate every outcome must pass. A decision enters VIR only after 4 tests: localization, distinguishability, stability, and irreversibility. Localization means that the outcome is not smeared across state space. Distinguishability means that it can be resolved from alternatives. Stability means that the outcome remains valid for the declared operational window. Irreversibility means that it is not just a reversible fluctuation that briefly looked like an output. This is the point where the difference between a raw output and a valid event appears. A circuit can create a candidate, but only these tests decide whether the candidate becomes an outcome. At the same time, it is important to be methodologically honest. This slide represents the full VIR ideal. I am not claiming that public benchmarks such as MLPerf measure all of these physical conditions. This is exactly why I later distinguish full VIR, task VIR, and estimated VIR. But this slide gives us the compass. Without it, we would not know what we are simplifying when we work with public data. And once we have the compass, we can ask what such a valid event costs. That is slide 4. The fourth slide turns the idea into energy accounting. If a decision is not only a symbol but a physical event, then it must have a ledger. VIR can be read as the rate of valid irreversible events divided by supplied power, or simply as outcomes per joule. The energy of one event can be decomposed into reversible work, entropic dissipation, and overhead. The overhead is often the most interesting part in modern architectures. In compute and memory, the array itself may be efficient, while ADC and DAC conversion, calibration, routing, refresh, readout, or output latching can consume energy that disappears from a simple TOPS per watt story. This is where the image of an expensive heater appears. A system can be extremely active, burn energy, produce graphs and numbers, and still fail to convert that energy into stable outcomes. In that case, part of the architecture behaves more like a heating element than a decision machine. The energy ledger is therefore not a detail. It is the way to say, let us show what we paid for the outcome and what we paid only for the path, the noise, the conversion, or the failure. And to avoid overclaiming, we need to separate the levels of VIR. That is the next slide. The fifth slide is, in my view, the methodological center of the talk. It separates 3 levels: full VIR, task VIR, and estimated VIR. Full VIR is the target physical metric. At that level, we would want trajectories, retention tests, state distinguishability, and entropy evidence. That is the level of a laboratory experiment. Task VIR is the publicly auditable layer. If a benchmark defines a completed outcome and reports energy, then we can compute outcomes per joule for that task. This is not yet microscopic thermodynamics, but it is an honest audit of the task layer. Estimated VIR is weaker. It is derived from TOPS per watt and declared operations per output. It can be useful, but it must remain labeled as an estimate. This separation prevents the biggest misunderstanding, that I am claiming MLPerf measures microscopic entropy. I am not. I am saying that public data allow us to audit one layer, and that this layer is useful as long as we do not dress it up as something stronger. That brings us to the public data themselves, namely MLPerf Tiny. The sixth slide shows how the public benchmark enters the work. MLPerf Tiny is not a physical microscope here. It is a public ledger of outcomes and energy. One completed inference that satisfies the benchmark qualification rules counts as one task layer outcome. The energy is the reported energy. The ratio of these quantities gives task level VIR. The work uses 27 public power results, 5 workloads, and a range from approximately 2.73 times 10 to the minus 2 up to 3.17 times 10 to the 4th benchmark outcomes per joule. This shows that the task layer is computable and comparable across public submissions. But there is also a boundary. From these data, I do not claim all thermodynamic conditions of full VIR. We do not see trajectories, we do not see all retention mechanisms, and we do not see microscopic entropy. We see a publicly auditable task and its energy. And because the task has meaning, we must not collapse all workloads into one table. That is slide 7. The 7th slide resists the temptation of a single universal ranking. Benchmarks invite us toward a simple order, first, second, third. But workloads are not the same type of physical event. Keyword spotting, visual wake word, image classification, anomaly detection, and other tasks have different semantics. They define the outcome differently, treat errors differently, and stress the physical architecture differently. This is why comparison within a workload makes sense. Within workload relative task layer VIRR preserves context. It does not say that one workload is generally better than another. It says that an outcome only has meaning relative to the task that requires it. A hallucinating bit is also always hallucinating relative to a requirement. A signal that is sufficient for a coarse indication may be unacceptable for stable classification. VIRR is therefore not an Olympics of electrical activity. It is an audit of outcomes in their own context. And once we compare outcomes, we must also show measurement uncertainty. That brings us to slide 8. The 8th slide reminds us that every number has a shadow. That shadow is uncertainty. If we report task layer VIRR, we also need to show measurement variability. Points with coefficient of variation equal to 0 do not necessarily mean a perfectly stable physical world. They may simply mean that the public data contain a single reported value or that spread was not reported. For highly energy efficient systems, this becomes even more sensitive. When we measure extremely small energies, the relative influence of instrumentation and measurement noise can increase. A number in a table may look very precise, but without spread, we do not know whether it is physical precision or merely precision of notation. Here the motif of hallucination shifts. Sometimes it is not only the bit that hallucinates, but our confidence. A benchmark without uncertainty may look hard, but be soft. Once we have outcomes, energy, and uncertainty, we can look at the most dramatic consequence. Architectural rankings can change. That is slide 9. The 9th slide shows a ranking reversal. Under raw 1/E, one system can look like the winner, but if we include valid output probability, rejection, retention, conversion, and control costs, the ranking can change. This is not a hidden empirical leaderboard. It is a controlled proof of concept. It shows the mathematical mechanism by which a raw energy advantage can disappear if outcomes are not stable or if their stabilization carries hidden energy cost. Here, we need to be fair. For a full application to commercial chips, we would need data that are often not published. Retention losses, conversion overhead, rejected transitions, and the exact stabilization window. But the mechanism matters. An architecture should not be rewarded for outcomes that do not survive their own use. If an outcome dies before it starts to mean something, it was not an outcome. It was a hallucinating bit with good marketing. To make this argument more than criticism, we need to know exactly where VIRR is lost. That is slide 10. The 10th slide turns VIRR into engineering diagnostics. It is not enough to say that a system has low or high VIRR. We need to know why. The ledger ablation shows components where outcomes per joule can be lost: compute, conversion, rejection, data movement, retention, and control. This chart is not a direct decomposition of an ML-perf power log. It is a component sensitivity model, and precisely as a model, it is useful. It shows where a designer should look. If conversion dominates, it is not enough to celebrate the array. If retention dominates, it is not enough to create a state quickly. If rejected candidates dominate, the system produces a lot of activity, but few outcomes. Here, the expensive heater becomes an engineering diagnosis. Energy leaves, heat appears, but valid decisions do not increase at the same rate. The next question is therefore, how long must the outcome survive? That is slide 11. The 11th slide brings time back into the metric. It is not enough to create an outcome. It must survive until the moment when it has meaning. Tau star is not an arbitrary penalty. It is a task requirement. Retention before readout, latch state lifetime, or application output hold time. When we tighten the stability window, relative VIRR decreases differently depending on the physical regime. A tight transition, longer settling, and a low barrier do not have the same profile. This is why the stability window must be declared. Speed says when something appeared. Validity says whether it survived until the moment of meaning. Without that validity, a fast bit can become only a fast hallucination, but stability is not the only filter. Next to time, we have noise and threshold choice. That is slide 12. The 12th slide shows that noise and threshold choice must not be hidden. In analog and stochastic systems, the outcome is often not far from the boundary. Once we change the distinguishability threshold, or the noise amplitude, we change the number of candidates that pass as valid outcomes. This is why one beautiful number is not enough. We need to report the stability surface. A single number can be fragile because it stands on one threshold choice. A surface shows robustness across regimes. Hallucinating bits are revealed precisely when you change the threshold of reality and they disappear. A robust outcome remains. A fragile candidate collapses. To show why this argument has a physical basis, we now move to the B-stable model on slide 13. The 13th slide shows the physical bridge underneath the whole presentation. A bistable potential represents a decision as motion in a landscape with two stable regions. The parameter h of t tilts the landscape, noise c of t introduces fluctuations, and the Langevin equation describes the fact that the transition is not a symbolic jump, but a trajectory. Logical abstraction says the output is 0 or 1. Physics says the state had to move through a landscape, overcome noise, settle into an attractor, and remain there. This model does not claim that MLPerf measures microscopic trajectories. It shows what full VIRR would measure if we had x of t, v of t, I of t, the protocol, temperature, accepted and rejected events, and forward and reverse trajectory probabilities. In other words, the task layer audit is the first floor. The bistable model shows what the physical basement of the structure would look like. This brings us to the validation ladder on slide 14. The 14th slide summarizes the most honest part of the work. Validation is not a single claim, but a ladder. Public benchmarks validate the task layer. Retention or resistive RAM data add the stability filter. Stochastic trajectories make it possible to test entropy production. And only a combined laboratory experiment moves toward full VIRR. This matters because a new metric must not pretend more than the data can support. VIRR should be stricter than older metrics precisely because it names the boundaries of its own evidence. In this sense, VIRR is not only a number, but a protocol of responsibility. It asks every outcome. Did you occur? What did you cost? Did you survive? Were you distinguishable? And do we know this or only assume it? Every valid outcome should have its physical birth certificate. And that brings us to the conclusion. The conclusion of the work is conservative, but its consequence is not. It is conservative because VIR is not meant to replace TOPS per watt, energy delay product, latency, accuracy, area, or endurance. It is meant to add a question that those metrics do not ask on their own. How much energy became accepted stable outcomes? The consequence is radical. Once we start counting outcomes rather than activity, the way we evaluate architectures changes. We stop rewarding mere motion and start demanding physical responsibility of decisions. Public data already allow a task layer audit. The next step is clear: raw trajectories from resistive RAM cells, noisy latches, analog memory arrays, edge inference processors, and stabilized measurement records. There, task VIRR can move toward full VIRR. If the audience should take away one sentence, it is this: computation is not activity without a body. Computation is a physical event that must pay energy, survive noise, and persist in time. Thank you very much for your attention. If you have any questions, I will be happy to answer them. For more detailed questions regarding the framework, the data, or the experimental validation of VIRR, please feel free to contact me by email. I will be very happy to provide a more detailed response. Thank you again for your time and attention.